Explainer. Today we are diving into something absolutely awe-inspiring, often devastating, and honestly, incredibly complex. We're going to break down exactly how a volcano works. So if you've ever found yourself wondering about the journey from those deep underground crucibles of fire all the way up to the explosive summits, well, you are in exactly the right place.
Okay, let's start with a quote from volcanologist Robert Decker that I think just perfectly hits the nail on the head regarding our fascination and, terror of these fire mountains. He said, "They are beautiful in repose and awesome in eruption. They hiss and roar. They smell of brimstone. Their heat warms, their fires consume." It really highlights the paradox, right? They're beautiful, but completely terrifying. I mean, every single piece of volcanic rock on Earth was born of literal fire and fury.
And honestly, because of that sheer, unbridled power, humanity has naturally blamed eruptions on the gods since antiquity. Take the Greek god of blacksmiths and fire, Hephaestus. The ancient Romans later renamed him Vulcan. They actually believed his underground forge was responsible for the fire and ash shooting into the sky, which, fun fact, is exactly where we get the word volcano in the first place.
We feared them for millennia, but today we don't have to rely on myths. Here's our roadmap for the explainer. We'll go from myths to magmatic roots, explore magma gas and viscosity, compare red versus gray volcanoes, look at eruptions and landforms, uncover the deadliest hazards, and finally look at how we monitor the warning signs. Section 1. Myths to magmatic roots. Let's look at the engine underneath.
So, the most crucial starting point is getting the distinction between magma and lava straight. It's kind of like a giant underground puzzle. It all starts as magma, which is molten rock that is literally sweated out of the Earth's mantle through partial melting, roughly 60 to 80 kilometers below our feet. It collects down there in these massive reservoirs. Now here's the kicker. It is only reclassified as lava once it actually breaches the Earth's surface.
Simple, right?
Moving on to Section 2, magma, gas, and viscosity. The chemistry of chaos.
Now here's the thing. Not all magma is created equal. When we talk about how a volcano works, its unique chemical makeup dictates exactly how it'll behave when it wakes up. And this chemistry of chaos really comes down to its silica content. Silica directly dictates the magma's viscosity, or basically its stickiness. Basaltic magma has low silica, so it's super runny. But on the flip side, rhyolitic magma has high silica, making it incredibly thick and viscous. We're talking up to 100 million times more viscous than water. And that stickiness, it traps gases, which sets the stage for some really deadly explosions.
So why does that stickiness matter so much? Well, think of it exactly like shaking up a warm bottle of soda. As magma rises, the surrounding pressure drops. This allows dissolved gases to form bubbles, a process called vesiculation. Now, if the liquid magma is runny, those gas bubbles just bubble up and escape super easily, giving you a nice, gentle lava flow. But if that magma is thick and sticky, those expanding gas bubbles get completely trapped. The pressure just builds and builds until, boom, the magma literally shatters, causing a massive, violent eruption.
Which brings us to Section 3, red versus gray volcanoes, effusive versus explosive.
This chemical fork in the road, the runny versus sticky magma, actually gives us a fantastic shorthand used by volcanologists to categorize eruptions worldwide. It perfectly divides our world's volcanoes. On one side, we have the red volcanoes. These feature effusive, flowing red lava, and you'll usually find them on mid-oceanic islands like Hawaii. Because their magma is so runny, they put on these beautiful, relatively safe, glowing shows. But on the other side, we have the gray volcanoes. Usually found near continental margins, their magma is thick and sticky. They don't just flow, they explode, literally blocking out the sun with these massive, terrifying plumes of gray ash and rock.
Section 4, eruptions and landforms, how these forces shape the Earth. So, over thousands of years, the type of magma actually dictates the physical shape of the mountain itself. Runny basaltic lava travels super far before it finally cools down. Over time, this builds massive, gently sloping shield volcanoes, kind of like Mauna Loa. It literally looks like a warrior's shield resting face up on the ground. Conversely, the sticky, explosive magma of a gray volcano, it doesn't flow very far at all. Instead, layers of viscous lava and shattered ash just pile up close to the vent. And that is what builds those steep, beautifully symmetrical, classic stratovolcanoes you've probably seen pictures of, like the Kronotski volcano.
All right, Section 5, the deadliest of volcanic hazards, specifically pyroclastic flows. Unfortunately, the majestic, picture-perfect beauty of those gray stratovolcanoes completely hides their capacity for absolute, terrifying destruction.
The number 700. This represents two horrifying metrics of the deadliest volcanic hazard on Earth, the pyroclastic density current. When a huge explosive eruption column loses its upward momentum and collapses, it creates a ground-hugging avalanche of hot gas, ash, and fragmented rock. These clouds can travel at mind-boggling speeds, up to 700 kilometers per hour, and they reach incinerating temperatures of 700 degrees Celsius. You can't outrun them, and you absolutely cannot survive them.
Because gravity pulls all that heavy rock and ash down the mountain slopes way faster than a hurricane, these flows are historically responsible for the most devastating volcanic tragedies. I mean, it was a pyroclastic current from Mount Vesuvius that famously buried Pompeii. Back in 1902, Mount Pelée sent a glowing cloud into the town of St. Pierre, entirely charring the city and killing roughly 30,000 people in mere minutes. Even modern volcanologists, who are fully aware of the danger, tragically lost their lives to a sudden surge at Mount Unzen in 1991.
But here's the thing. The hazards aren't just local. Beyond incinerating everything in their immediate path, massive Plinian eruptions can inject incredible volumes of volcanic gas straight into our stratosphere. The global stakes here are immense. The sulfur dioxide converts the sulfuric acid droplets that actually reflect sunlight, which causes temporary global cooling. Meanwhile, the millions of tons of carbon dioxide they pump out is a greenhouse gas, which over long geologic timescales promotes global warming. So yeah, they literally have the power to alter the climate of the entire planet.
Section 6. Monitoring the warning signs. Predicting eruptions before they happen.
So, knowing all of this immense, globe-altering power, how do modern scientists actually protect us today? Well, they look for the warning signs that magma is on the move. Magma doesn't just sneak up to the surface quietly, it has to fight its way up, and we can measure that fight. Scientists monitor for seismic swarms, which are hundreds of tiny earthquakes as magma breaks rock to rise. They also listen for harmonic tremors, which is literally the hum of fluid magma vibrating through underground pipes. We even use satellites and lasers to measure ground deformation, watching the surface of the mountain literally bulge and swell as pressure builds. And, crazy enough, we even watch water wells. Sudden drops in underground water levels can mean rising magma has cracked the surrounding crust, draining the water away right before an eruption.
By reading all these signs, we can evacuate cities and save countless lives. But as we wrap up this explainer, I want to leave you with a bit of a provocative thought to ponder. We've spent a lot of time today talking about the hazards, the destruction, and the sheer terror of volcanoes. But consider this. It was volcanic degassing over billions of years that actually generated the Earth's atmosphere and oceans. Lava flows built the very land masses we're standing on right now. And volcanic ash continually revitalizes our soil so we can grow the food we eat. So though they're infamous for their destruction, could we even survive on a planet without the fiery heartbeat of volcanoes? Something to think about.